number 5 is on partial fractions. So there are lots of different ways to integrate things. So we're going to be learning, like we've already learned how to do like regular integration by the power rule, use substitution. We're going to learn something called integration by parts, and we're also learning this, which is partial fractions. Oh, and one more, trig substitution. So there's several ways to integrate things. So sometimes it's hard to know exactly what process to do. So today we're learning about partial fractions. So it says add the following fractions in order to get one fraction. So this is kind of a preview. And yes, I hope you know how to do this from Algebra 2. All of you were like, oh, this is easy. So we're going to multiply by x plus 2 over x plus 2. We're going to multiply by x plus 1 over x plus 1 to get common denominators. When we do, the first fraction is 3 times x plus 2 all over x plus 1 times x plus 2. And the second fraction has the same denominator. So we just combine our numerators, 1 times x plus 1. So we get a total on the numerator of 3x plus 6 plus x plus 1 all over that same denominator. Sometimes I'm lazy and I just do little quote marks.
Oh, that's what those means.
So I get 4x plus 7 all over x plus 1 times x plus 2. And you might also see the bottom multiplied out. It might look like x squared plus 3x plus 2 on the bottom. Okay? Makes sense? Well, sometimes you don't need both denominators. So I don't need to multiply number 2 by x squared minus 1 over x squared minus 1. Do you guys all see that? What do I need to multiply the 5 over x plus 1 by? Just x minus 1 over x minus 1. And that's because the second denominator factors into x plus 1 times x minus 1. So we already have the x plus 1. We need another x minus 1. Do you guys understand? So we're going to multiply this 5 over x plus 1 by x minus 1 over x minus 1. So when we do, we get 5 times x minus 1 all over x plus 1 times x minus 1. And then we also have that plus the negative 2. So combining everything, we get 5x minus 5, but then minus another 2 would be minus 7 over, and you could FOIL it out, or you could leave it as x plus 1 times x minus 1. So you could also have 5x minus 7 over x squared minus 1. Does this make sense? Okay, so don't go too big if you don't have to. Like, only use the denominators that you need. So on this next one, the x squared minus 4 does factor. It factors into x plus 2 and x minus 2. But that doesn't really help us in this case because the other denominator is just an x. Okay, so what we multiply the first one by is x squared minus 4 over x squared minus 4. So it changes into x times x squared minus 4 on the bottom, and then 1 times x squared minus 4 on the top. Did you guys see that? And then plus, what do I have on the other one? X, because I'm going to multiply by x over x, right? So we just get a plus x. So this works out to be x squared plus x minus 4 all over, if I multiplied it out, x cubed minus 4x. Okay, does this make sense? Yeah, Ethan.
Wouldn't this be the same as like the last one? You could just do
X times x minus 4.
and then you wouldn't have to do x.
No, because it's not x squared minus 4x, right? Does it make sense? If you had x times x minus 4, does it make sense? Then you have an extra x in there. All right, so what we're doing in this section is not what we just did there. I'm glad that makes sense to you, but we're going in reverse. So we're going to have things that look like this, and we're going to have to integrate it.
Oh.
And it's like, wait, how do you integrate that? Well, you break it down into things that look like this, and we integrate those instead. Okay? So that's our whole goal, is to slowly break things down. So it says sometimes in calculus we have to break large fractions into the sum of simpler fractions. So these simpler fractions are called partial fractions. And the process is called partial fraction decomposition. So the sum of all those partial fractions. Okay, so there are certain rules. Anybody remember any of these rules?
Oh.
Not so much. Okay, so I think I'm just going to give you an example on these because it's hard to do, like writing it out all in symbols. So it says, number 1, the denominator is a product of distinct linear factors. Okay, so if you're able to factor the denominator into something like x plus 1 times 3x plus 2 times x minus 5, Okay, those are all linear factors. They're all x to the first, right? So that means when we break it apart into separate fractions, we're going to have their pieces, x plus 1, 3x plus 2, and x minus 5. And our numerator is at most 1 degree less than what we have. So what's 1 degree less than x to the first? X to the 0, which means it's just a constant. So we would have something that was up here, we don't know what was up there, and it's going to break into a constant over x plus 1, a constant over 3x plus 2, and a constant over x minus 5. Okay, the reason it's 1 degree less is because if it isn't 1 degree less, if I had like 3x minus 5 over 2x plus 7, I can actually simplify that down using long division. So we'll talk about the long division ones. Right, all your eyes. Oh my god, long division.
Wow, that sounds exciting.
All right, so the next one says the denominator is a product of linear factors, some of which are repeated. So maybe you have something like that x plus 1, but you have it to the third. And then you have a 2x minus 5 or something as well. Okay, so what happens in this case is you need to repeat it the number of times that we have it. So we have it 3 times. So we're going to do x plus 1, basically to the first, x plus 1 squared, and x plus 1 cubed. It's kind of annoying. So we're going to do x plus 1, x plus 1 squared, x plus 1 cubed. And then the last denominator, what do you think it's going to be? 2x minus 5. Okay, and I told you that at most it was 1 degree less on top. But on something like this x squared one, we don't write like ax plus b. That would be 1 degree less. Instead, we ignore the squared. So it's like we ignore the square and then we do the 1 degree less. Okay? So the numbers on top are still a, b, c, and d. Just constants, some kind of number there. This will make more sense when we do the examples, so don't freak out if you don't totally understand right now. All right, and then number 3, it says the denominator has irreducible quadratic factors. That means quadratics that cannot be factored, so things that have x squared that can't be factored. Who can give me an example of something that has x squared, but it can't be factored? Nope, x squared minus 1 is factorable.
X squared minus 3.
That can be factored into like x plus the square root of 3. X squared plus 3, that works. X squared plus 3, x squared plus 9, things like that would have like I solutions, right? So let's say we have on the bottom x squared plus 1. Or we have like x squared plus 9. These are irreducible quadratics. So it doesn't matter what's on the top. When it factors, or when it breaks down, it's going to be that same denominator, x squared plus 1, and the other one, x squared plus 9. But now what's 1 degree less? So we had an x squared. 1 degree less is going to be x. So we're going to have a times x plus b. So this next one is going to be c times x plus d.
Oh,
You remember this?
it looks familiar. Never figured it out.
Wait, how come we did that here but not on the other two?
Because those ones were, we ignore the square and we ignore the cube, and then we just do 1 degree less than those. So, does that make sense? So when they're repeated, we don't worry about those squares and cubes. All right, so what if it has repeated irreducible quadratics? So if it had x squared plus 1 squared, or x squared plus 9 cubed, that's the annoying ones, right? So what do you think are, how many denominators do you think we're going to have? How many
5.
fractions? We're going to have 5. So it's going to be like x squared plus 1, and then it's going to be x squared plus 1 squared, and then it's going to be x squared plus 9, and then it's going to be x squared plus 9 squared, and then it's going to be x squared plus 9 cubed. Shoo, that's a lot. And then they're all ax plus b, cx plus d, ex plus f, gx plus h, ix plus j. That would be ridiculous. I'm not going to give you one that's that hard, but that's how it would be set up. Does that make sense? Do you guys get it? Okay. So the first couple examples I have are just like setting it up, and then we're actually going to find those coefficients for a, b, c, and so on. So it says, write the form of the partial fraction decomposition of the function. Do not determine the numerical value of the coefficients, though. So we're not going to find a, b, and c. Sorry. Okay, so first we're just going to decide what our 2 denominators are going to be. So you're going to try to factor, which I think it's already factored, right? So our 2 denominators are going to be x minus 1 and x plus 2. So it's going to be x minus 1 and x plus 2. So if you're checking your homework with a friend tomorrow and you're like, oh, I did x plus 2 first and then x minus 1 second, so my a and b are different, that's okay. Like your a might be different than the b of another, like the a of another person. Your a might be their b. But as long as your final answer is the same, that's okay. So like this next one, do we have repeated ones? Yeah. So x is actually repeated. It's x squared, right? So we're going to do x, and then we're going to do x squared, and then we're going to have x squared plus 4 one time, and then we're going to have x squared plus 4 two times. So remember, on the repeated factors, we ignore their power for now when we're doing our a's, b's, and c's on top. So ignore those powers. So what do we think are on top of, what's on top of the x? A. What about the x squared? B, because we ignore that repeat. Cx plus d. Ex plus f, right? And if you mess up and let's say on x squared you put bx plus c, it's totally fine because what will happen is b will end up being 0 when you do it. Okay? All right, so let's try this process. Let's try to break down things that look like that, like 4 over x squared minus 4, because we don't know how to integrate that, right? How do you integrate something like that? I don't know. Nope, it's not a u substitution. Why can it not be a u substitution? Because we need an x somewhere, right? So we can't do it with a u substitution. So we have to learn all these different methods for integration. Yep. You could, yeah, but then you still have 1 over x squared minus 4, and how do you integrate that? All right, so here we go. So it is by this method, yes. So, all right, so I factor in that. And then I write it with my x plus 2 on the bottom, guys, and my x minus 2 on the bottom. Okay, it doesn't matter which order you put them in, but we're going to have an a on top of one and a b on top of the other. Okay, so now we kind of go back to what we were doing at the beginning of class, that little warm-up that I gave you. So if I was combining these to get common denominators, I would need to multiply the a by x plus 2 over x plus 2, right? Not x plus 2. You guys were like, yeah, that's right. X minus 2 over x minus 2. That other denominator, right? Do you guys see what I'm saying? Like I'm trying to get common denominators here. So I'd multiply by x minus 2 over x minus 2. You see it? What would I multiply the next one by? X plus 2 and x plus 2. Right? So I'm going to end up getting the numerator as b times x plus 2 over that same thing, x plus 2 over x minus 2. Okay. Yeah, we're going to in a second. But all of this is equal to 4 over x plus 2 times x minus 2. So what happens is these denominators, useless. We don't worry about them. They're the same. And we have this equation where 4 is equal to ax minus 2a plus bx plus 2b. So when we combine our x values, well, what are our two x values? We have a and we have b. Do we have any x values on the left-hand side of our equation? No. So that means that a and b have to combine to be 0.
Wait, why is that?
Because it's like we have a 0x there. And then same thing here. If I have this 4, well, these are now numbers, right? So what's my other equation? 4 is equal to negative 2a plus 2b. So you look for the things with x's, set them equal to anything with x. Look for the things that are just numbers, right? Those are numbers, and set it equal to the number. And if you had an x squared, you'd find the things that have x squared, and so on. Okay, so what do we have here? System of equations. Good thing we just practiced this with projectile motion, right? So we can solve for a. We can say, oh, a is equal to negative b. And then we can replace a with negative b. So we get 4 equals 2b plus 2b. So 4 equals 4b. So we get b equals 1. So what's a then? Negative 1. So what we've done is we've taken something that looks like 4 over x squared minus 4, and we've written it as what? Go back up there. way back up at the top here. How did we write it? A is replaced with negative 1. So negative 1 over x plus 2 plus 1 over x minus 2. So this right here that I have in the box is equivalent to this. These are the same thing. I know they don't look the same, but they are. And would we know how to integrate something that looks like that, like 1 over x minus 2? Like something like this? Yeah, it involves the natural log, right? Yeah, we know how to integrate that. We've done that. All right, so let's try the next one. So we're going to factor the denominator. So if you notice, it's going to be 2x plus 3 and 2x plus 3. In other words, it's 2x plus 3 squared. So this is one of those ones that has a repeated factor. So when we break it apart, we're going to have like a 2x plus 3, and we're going to have a 2x plus 3 squared. And on top, we're going to have a, and you could do bx plus c, but every single time you do that, you're just going to see that b will be 0. So it's really just plus b. So we don't do bx plus c. Because if you do it the long way and you're like, oh, I'm going to make it bx plus c, then you have to find another variable. So it's a system of equations with 3 variables. So it's pretty complicated. You need 3 equations to do it. But every time you do that, you'll get that this bx goes to 0. Like it's 0 anyway. So it's really just like a number over. So we just write a b. Yeah, Jordan?
Why did we square the second, like the under part?
Because this is one of those ones where it's a repeated factor. So it's like, let's see, linear factors that are repeated. So we did this. We wrote it out like 3 times or 2 times or however many times we had.
And the first one was just the first.
They weren't repeated. They were just listed
So it
one
was
time
the
each.
first one.
All right, so if I was getting common denominators, I would multiply the first one by 2x plus 3 over itself, 2x plus 3. So what would my entire numerator be?
2ax
Plus 3a plus b. And what's it all going to be set equal to?
2x plus 3 squared.
Just 2x.
Going back up here. Oh, I thought you meant under. Sorry. 2x is equal to that. Right, so we see it?
So whatever our original numerator is, we set our new numerator equal to our original numerator. All right, so now we're lining up everything that has x. So we have a 2x, we have a 2ax, and we don't have anything else. So because of that, we could say 2x equals 2ax, but we actually leave off the x's. So we just say 2 is equal to 2a. Well, that was nice. What's a? 1. All right, and then our 3a plus 2b, or sorry, 3a plus b is equal to our number, right? Well, not what number is over here? No, it's equal to 0. There's nothing over there, right? Equals 0. Are you saying you already found it? Are you one step ahead of me? I was wondering where you get -3. So b is -3 then. Yes. So our final answer is 1 over the 2x plus 3 and -3 over 2x plus 3 squared. And we would be able to integrate both of those because the first one would involve a natural log, right? And the second one would involve this u substitution. The first one actually involves a u substitution that gives you a natural log, but does that make sense? We know how to integrate those. Okay, is it making sense? All right, so let's try the next one.
Oh, I hate cubes.
It's not the sum or difference of cubes, it's just x cubed here.
Oh.
So we're going to pull out an x, and we have x squared plus 4. So we have a linear factor, which is just x to the first, and we have a quadratic factor that's irreducible quadratic. So if I'm breaking it apart, I have an x on the denominator, and I have an x squared plus 4 on the denominator. So I'm going to have a, and I have bx plus c.
Wait.
So this is the first one that we've had 3 variables, a, b, and c. Okay, so think about how we get common denominators. So this first one, we're going to multiply our a by x squared plus 4 over itself. So we're doing x squared plus 4. And then the second one, we're multiplying by x over x. All that entire numerator is going to all be equal to 2x squared minus x plus 4. So I'm just leaving off the denominators because they'll be the same. So we get ax squared plus 4a plus bx squared plus cx is all equal to 2x squared minus x plus 4. Okay, so again, we're matching things up. So we have our x squareds. So we have 2 is equal to a plus b. We have our x terms. So negative 1 is equal to c. And we have our numbers. 4 is equal to 4a. Still with me? I think it's positive 4, isn't it? So a equals 1. Did I make a mistake?
Wait, why is -1 equal to c? Oh, because it's an x.
Those are the x ones. Yep. So we have a is equal to 1, c is equal to negative 1, and then we can get b by plugging in a is 1. So I think b is also 1. So in the end, our a was over x, so we have 1 over x, and we had bx plus c, so we have 1x minus 1. So we have x minus 1 over x squared plus 4. Okay, so that's our partial fraction decomposition. Okay. Next up, part D. So think about how to separate it with the A's, B's, and C's. Are you guys trying it? So the first denominator is x minus 1. The second one is x minus 2. And the last one is what? You got it. Numerators? B, C. Yep. You still want to do CX plus D, don't you? I did too when I first learned this. I was like, why not? Why can't it be CX plus D? But I was just making it so hard on myself. We want to do the easier one, right? All right, so we think about what each denominator needs. Now this is a tricky one, and there is a shortcut to doing this. It's very exciting. Okay, so in the last one, whoops, did not mean to do that. I'm going to draw a line. Jeez, I'm still trying to draw a line. Making my YouTube viewers very dizzy, I'm sure. So I meant to, so on the last one, you guys notice how like we got A, B, and C pretty easily. Okay, let's look at what this would involve on this one. So our A would be multiplied by x squared, or x minus 2 squared. Our B would be multiplied by, well, it needs an extra x minus 1 and an extra x minus 2, right? And our C would be multiplied by x minus 1. And this all is going to equal that other denominator, the 4x squared. Oops, that's a square. So I don't even want to do the algebra behind this. Do you guys want to like FOIL that out, combine your like terms? Yeah, it's kind of annoying, especially if you had like more than one repeated factor. If you had x minus 2 cubed, it just gets to be a mess. Okay, so here's a shortcut on doing this. This should work for any x value that we plug in. What would be convenient x values for me to plug in? X equals 0. That's a good one. So if I plug in x equals 0, well, it's not really that good. Let's plug in a better one. 1. Why do you say that, Michaela? It's 1 after. It is 1 after 0. But 1 is nice because of this here and this here. So if I plug in 1, I get 4 is equal to a times negative 1 squared plus b times 0 plus c times 0. So I end up getting 4 equals a right away. Do you see it? You can. You can do it for any x value. So what's another good one?
2.
Oh, you got to figure it out now. So if I plug in 2, I get 4 times 2 squared equals 0 plus c times 1. So c equals 16. So we're almost there. We just have to find b. So that's when I would probably plug in 0 then, because we don't have another really, really good one that's going to cancel half of them. So if I plug in x equals 0, now I get 0 equals a times 4 plus b times -1 times -2 plus c times -1. So I have 4a plus 2b minus c is all equal to 0. Well, luckily we have a was 4, right? B was, we don't know. C was 16. So what do we get for B? 0. So it's like that middle term is just gone now. So putting it all together, we have A, which was 4 over x minus 1. The B part goes away. This all is gone. So then we have plus C, which was 16 over x minus 2 squared. That's our partial fraction decomposition. Okay, so what do we do when the denominator is like a certain degree and the top isn't something smaller than it? It should always be smaller than the denominator on top. If they're equal, we also do this method that I'm going to show. So we do long division. So if I have something that's x to the 4th over something that's x cubed, I want to break it apart. Okay, so we do our long division. I know you guys are all like, ugh, long division. It's not that bad. Oh, you'll be fine. It'll take like 2 steps. Okay, so here we go. So what do I multiply by x cubed by to get 2x to the 4th? 2x. I take that 2x, I multiply by everything in the quotient, so I get 2x to the 4th, not quotient, in the divisor. 2x to the 4th plus 4x cubed minus 2x squared minus 4x. I draw the line and I change the signs. You almost remembered it. And you'll see that most of it goes away. How exciting. We're left with 5x plus 7. So what does this mean? That our remainder is 5x plus 7 all over x cubed plus 2x squared minus x minus 2. So now we do the partial fraction decomposition here. PFD. That's a PFD. PPD. FD.
You're such a child.
PFD is like a life check.
All right. So really, we're just going to have a 2x out front of everything. So now we just factor that x cubed plus 2x squared minus x minus 2. Well, how do we factor that? By grouping. So x squared times x plus 2. I'm glad I can bring back all these Algebra 2's finest moments for you guys.
Go back to this.
So I pull out the x plus 2, and I have x squared minus 1, which factors into x plus 1, x minus 1. So we end up getting the 2x out front, and then we have plus a over x plus 2, plus b over x plus 1, and plus c over x minus 1. And then you can continue from there. Really, all you're worried about is this portion right here. You can ignore the 2x till the very end. Can I write etc. and you're good to go? All right, so then the last little bit says, well, how do you find the antiderivatives of these things? So that's what I was kind of talking about. So if I go back to 2a and 2b, and I was asked to find the antiderivatives of these, then we just kind of break it apart into the separate integrals. So we break it apart into a negative out front, 1 over x plus 2 dx, plus 1 over x minus 2 dx. And we can think about the u substitution, but if you let u equal x plus 2, do you guys see how we don't gain like an extra constant or anything out front? So we're good. So this ends up being a natural log equation. So it's going to be negative natural log of the absolute value of x plus 2 plus the natural log of x minus 2 plus c. Okay, that would be it. But then something like this, we would gain from our u substitution, what would we gain? A 1/2 out front, right? So I'd have du equals 2 dx. So I'd have a 1/2 du equals dx. So I'd have the integral of 1 over u, which does make the natural log. So I'd have a 1/2 out front, natural log of the absolute value of 2x plus 3. That's going to be the first part. And then this other part, if I integrate it, it is a u substitution as well. So it's also 2x plus 3. So I'm going to have a 1/2 out front, and then I have negative 3 over u squared du. So do you know how to integrate that? So pull the negative 3 out, and then you have u to the negative 2 du. So what do I get when I integrate u to the negative 2? I know I'm like killing your brain right now. U to the negative 1, 1 over negative 1. So it's going to be just plain 3 over 2 up front. So we're going to have plus 3 over 2 times 1 over 2x plus 3. Let's see. Well, the minus, I gained another negative from the antiderivative of u to the negative 2. So it's u to the negative 1 times 1 over negative 1. Yep, so that would be how I integrate that. And then, you know, the AP test, like if you guys took this BC calculus, you could combine these with division because one of them has a minus. There's things you can do to combine those and so on.
Shouldn't it be a negative? Because if you had 2x plus 3 to the negative 1 and you brought that down to be minus,
I think I'm right. Because this is going to be
oh yeah.
u to the negative 2, which gives u to the negative 1, 1 over negative 1, and then you're multiplying by that negative 3 over 2, right? All right. Make sense? So that's what that section's on. So is that kind of a review? Did you guys